thank you, Professor Pitsch, for coming here, give us a lecture. I just want to speak on behalf of all the attendees here. It's from what I heard, it's just marvelous lectures, and that's sort of expected from you, but still, it's that's why we got you involved to do that. But that's again, I repeat, it takes a lot of effort to put this together. But it's not trivial. A person like him he's busy. He's being in demand in many things. But the important thing, I think we should all learn from the senior people in the community is how they, look at the education and the communication of ideas to the younger generation. We put that as top priority, and I'm sure that's how Professor Pitsch feels like it, and he puts in the time. And we hope that not only you learn the thing, the knowledge, but also learn how we look at things, how we value, the prioritization of the things, okay? The passing out of the knowledge. So we thank you very much, Professor Pitsch, for coming here.
Okay.
So let's.
All right. Good, thanks for the nice words, Ed. So let's get back to work.
Yes.
So first thing we have to do is, of course, to discuss the game yesterday. Very good. I'm glad this time I was on time. You see, it makes a difference. The best loss ever. That's right. So outcome was good for both teams. As you know, I lived in this country for 12 years. And so I'm a little torn. My son is American. He's very torn when he watches these games. And so it was a good outcome for everyone. Good. So that said, let's get back then to the less important things. Combustion, to this, or let's say the second important thing, second most important thing. So yesterday we started looking at modeling, and we reviewed some of these more simple models that you find in commercial codes, and we said maybe what's the idea, what should it be used for, what should it not be used for, and so on. And so I want to also show you some of the more advanced models. Some of these are also available in these commercial codes. And all these models that I'm showing you now, some of these models up here, they are right in an asymptotic limit. But some of the models also, they're empirical. They're just, put together, let's take this or that, and that's okay. But the models I'm going to show you now, they all, they're very much based on the fundamental theory. That's actually a good thing. If you have, turns out, if you have whatever, model it doesn't matter if it's a combustion model in fluid mechanics, model in combustion, or model in some other fields. As long as the model is based on the fundamental theory and the true equations and is rigorously derived for some limit, you will mostly see that these models, they are not only valid in the limit for the exact assumptions you made. Usually they're applicable over a wider range. They extrapolate really well in the regions also where they actually maybe that they're not derived for. So having something that's based on the fundamental equations is always worth a lot. So think of that when you, maybe some of you, do modeling also. Think of it. Try to stay away from the empirical side and try to always go back to the governing equations and try to, make assumptions in the governing equations that gives you models. And then these models, if they're based on first principles, then they should also be, they should be extendable or extrapolatable beyond what you might have assumed. Okay, so last time we talked about, or I showed you this, again, which is mostly follows the, Steve Pope's book on turbulence, where we introduce here terms like probability, joint probability, and so on. And I want to, so I said the cumulative distribution function That is just so we measure with probability, we measure a random variable smaller than a sample space variable. The sample space variable is a set value, let's say it's 5 meters per second, and then we do an experiment, and we measure how often is the velocity larger or smaller than 5 meters per second, and let's say we can say then, well, the probability is 30% that the velocity is smaller, okay? And if you let that sample space value, which now we say is 5 meters per second, if you make that an independent variable in a function, in a probability function, then this cumulative distribution function gives you probability for each single value of this sample space. That's the cumulative distribution function. And so it's very obvious for the sample space variable minus infinity, the probability should be 0, right? Because no velocity is smaller than minus infinity. And for the sample space variable equal to plus infinity, it should be 1, because there's a 100% chance to find a velocity that's less than infinity. So this is this cumulative distribution function. And you see when you do experiments, you will find most of the experimental points where the slope of this thing here is largest, okay? And so because of that, maybe it makes sense to take the slope of this function as something we want to look at. That's a probability density function, it's just the slope of this function. And you see then this is largest where you get most of the sample points, okay? So then, because this is the derivative, if you take the integral from one point to the next, that gives you the probability to find a value within this range. So that's why this makes a lot of sense. And interesting is also then, and that's the one thing I wanted to show you here, because we will use that a lot, that if you have this PDF, the PF here is the PDF probability density function of V, and you have some function Q, which is only a function of V, then you can compute all moments of this function with this formula, okay? So if you want to know the mean of that function, then it's just the function times the probability density function and then integrated, from minus infinity to plus infinity. That gives you the mean of that function. So for example, you have velocity, okay? And you want to know, and you have the PDF of a velocity, and you want to know u squared, the variance. For example, the variance, u prime squared, then that function here would just be, so if I want to know u prime squared mean, then this function q would be just u instantaneous minus u mean squared, okay? Because this u prime squared. And now if I want the mean of this, be the mean of this, then this is just the integral of this function u minus u bar mean squared, and then times f of u, f of v dv, just to make sure we distinguish here between the sample space variable and the random variable, but that's a minor detail. But so anytime we have a function of a value of a quantity and we have the PDF of the quantity, we can use this to get the mean. That's the important point. Okay. Okay, so let's see, this is what I was just showing you. Okay, so now the one of the models that people talk about a lot is the transported PDF model, and I just want to give you the idea here what this is. As a matter of fact, you could, let's say, you have the joint probability, and that's the nice thing about this. If you have the joint probability f of all mass fractions and temperature, this is a high-dimensional function, right? But if you have this function, then it's very simple. Then you can get everything you want, okay? from this, using this, I can get the mean temperature, the mean mass fractions. I can get all the correlations between the mass fractions and temperatures, everything you want, okay? So if you know this function, everything's good. So you might think, why don't we just write a transport equation for this function and solve that transport equation, okay? And so that's what the PDF transport equation model does. It actually writes an equation for one-point statistics. That means you could also go a step further. You could say, I want not only the joint PDF of all scalars, I want the joint PDF of all scalars at 2 different points at the same time, okay? Then that way also you would see what the local gradients are and things like that. Or you could say of the values and their gradients or something. That would be more than 1 point. But here we do 1 point, 1 time statistics, and then we can derive a transport equation here. Steve Pope was the pioneer developing this method, wrote several papers, also review papers on this, and there are some earlier versions here of this method also. But anyway, so this would be the equation here, and you can see in some degree it looks very similar to the equations we had before. You have a time-dependent term, you have this convection term here, and then you have a few other terms. Here's a chemical source term somehow, and so on. So in a sense it is similar, but so what P here is what I call F here. But what's interesting is that this is a very high-dimensional equation, okay? So you see that this P itself is a scalar, because it gives you the probability density of the joint PDF, of the joint probability to find all these values, okay? Or think in terms of probability, not probability density function. The probability itself is a scalar value, and it is a scalar that tells you what is the likelihood, what's the probability of finding certain values of all these variables at the same time. Okay? So one thing that's interesting now is to see that if I want to look at the probability of some variable, let's say a mass fraction, okay? The probability of a mass fraction as function then of this mass fraction, then maybe this is the probability, whatever, okay? So here's 1, so it's never larger than 1. I mean, there's no probability to find a value larger than 1 and so on. So, but if you say, okay, I want a joint probability of the mass fraction and the temperature, okay? Then you see this is a 2-dimensional function. This would be temperature, and this would be now the mass fraction of fuel, and maybe, you find something that looks like this. Is large probability, smaller probability, and so on. Okay? So this is a scalar value in 2 dimensions. Okay, 2 coordinates. Now, if you have a typical methane mechanism, take the GRI mechanism, maybe some people know this, has like 30 species. So this plus temperature, this would be 31. So now we have a scalar function in 31 dimensions, okay? So it's a very high dimensional space. So if you look at this equation here, then you see we have a space derivative, so this would be 3 dimensions, plus, and then we have these derivatives here in these scalars, and here also in velocity, and that gives you like let's say a 50-dimensional space, okay? So that's the big difference between this equation and the equations that we usually know. So here, this is the joint PDF now of all the scalars, all mass fractions and temperature, and of all the velocities, of all 3 velocity components, okay? So if you have all this, even if you have this, you even have the scalar fluxes and all of this. If you have the velocity here, you can also get the scalar flux and these quantities. Okay, good. So let's look at what this is. The first 2 terms, of course, are obvious. Then there is a term here that represents transport in the velocity space, because now our space is not just three-dimensional physical space, our space is 50-dimensional, because 3 dimensions in space, 3 dimensions in the velocity directions, and then whatever, 35 directions in the combustion scalars. And so you have transport in physical space, transport in velocity space, and then here you have the chemical source term. Now this is interesting because, well, maybe we'll come to this on one of the next slides. Set here. So what's interesting about this is that usually when we do combustion modeling, then modeling the mean source term, that's usually the biggest thing we have to do. So we said very nonlinear and all of this. And what's interesting here is that this term is in closed form. It does not need modeling. The chemical source term does not need modeling in this model. Because here the chemical source term, that is a function only of all the species and temperature. Okay, and you see this is a function of species and temperature. This PDF I know, and so I can just take this derivative in this composition space, is very easy to take. So this can just be evaluated. And then we have this term here now is, let's see. This one here is transport of probability in the velocity space by here viscous stress and pressure. And so this here for us is now not so important. But the last term here, that is transport in reactive scalar space by molecular mixing. Okay? And so molecular mixing, is that important? Yes, it's very important, because remember the molecular mixing in combustion, that is what makes fuel and oxygen come together on a molecular level. So that term, for fast chemistry, that term really determines the reaction rate. Okay? Now here's the problem. This term involves, see this term here, just involves the values, the mass fractions and temperature itself. And so this can be evaluated, and you can also take the derivative in this space. But you see this one here involves gradients of species. The only thing we know from this model is the probability of finding a certain value, let's say of temperature, at this point, and we know the probability of finding a temperature at that point. We don't know what the joint probability is of finding a temperature like this at this point and like that on that point, which we would need to evaluate the local gradient. The gradient can only be determined if I have the joint statistics of 2 points. If I have just probability of finding a certain value here and probability of finding another value here, I don't know what the likelihood is, to find two certain values at the same time. So that's why this term here needs modeling. And now this is the main modeling challenge for combustion. This is the main modeling challenge for this model. Okay, so there's a lot of text here. Maybe we'll skip over this. So there are different models that have been proposed for this. They're not listed here. The simplest is what's called mixing by interaction with the mean. And all these mixing models, the terms that model this term, they are only, or they are formulated in the framework of the numerical solution. Okay? So let's first look at the numerical solution of this equation, and then maybe we talk about the mixing models for 1 minute. You have an equation now which is three-dimensional in space. So you can discretize this in space. Okay, you take 100 points in each direction, and then you have 100 times 100 is 10,000. Have you million points? Okay. But now the problem is, again, you have also basically coordinates in this so-called state space. And so now you have 50 directions, a 50-dimensional space. You can't discretize this, okay? Because you take even a 5-dimensional space, 4-dimensional space, is hard to discretize. So What's done here then is to use a totally different method that was also here introduced by Pope to solve these equations. That's the so-called Monte Carlo method. And what you do in the Monte Carlo method is well, in a sense, it's this. You can take this PDF transport equation and you can write it as a set of stochastic differential equations, let's say single-point stochastic differential equations, and then these are solved by introducing the concept of notional particles. So what you do is you have a particle, and that particle has all the properties of the flow. A particle is not a real particle. It's called a notional particle because it's just a thought-of particle. It has no mass or so. So you say you have a particle here, and that particle has these mass fractions, this temperature, this velocity, and all of this. And then, you evolve the particles according to these stochastic differential equations. Here, for example, this is the position of the particle is equal to u times dt. That makes sense, plus a diffusion term here, or this is a diffusion term. dw here, this is a random walk term that considers diffusion. So what you do then is you solve millions of these individual particles, you let them go with this equation through space, and then integrating this equation here, for example, this is the mass fractions, they are equal to the source term dt, or a change in the, or integrate this, then you have the change in the mass fractions is the source terms times, or integrated over time. That makes sense. And then this here is the mixing. I'll talk about this in a minute. But so you evolve these over time, and then when you want to know the PDF at one point, you take that point, you take a little volume around that point, and now hopefully you have a million particles in that volume around that point, and then you just, from all these particles, you build a PDF. Okay, you do a binning process, let's say, and you build a PDF, and that gives you the probability density function. So that's how the solution of this works, and that's beautiful because you can imagine if you have infinitely fast reaction, then in that 50-dimensional space, all particles, they must evolve along one line. Forget about the velocities, but just in the composition space, mass fraction and temperature, because for a certain mixture fraction, which is the coordinate along this line, for a certain mixture fraction, there's only one solution. There's no ambiguity anymore in the solution. So in this 50-dimensional space, you walk along a single trajectory. And so you don't need so many particles. You don't need to resolve this 50-dimensional space. You only need to know, you need to resolve what's truly happening using this Monte Carlo method. Okay, so that's why this works. You kind of reduce this 50-dimensional space with this particle method, which then has particle only in a smaller dimensional space within this 50-dimensional space. So, right. So that's how you solve this, and it's fairly expensive to do this. Because of mostly this equation, let's say you have 50 chemical species, you need to solve this, for these millions of particles you might have. At each time step, you need to, this is an ordinary differential equation, so you need to have and usually they're stiff, so you need a stiff ODE solver to solve this, and there have been methods to make this more tractable. One is the what's called ISAT. I think we had this earlier here, which is basically tabulation methods that you can use to save some of these numerical integration steps. Okay, so you just because S is just a function of the local composition. If you have the local composition, you can go in your table and see, have I done this integration before? And if yes, you just take the solution that you had before. So that's the so-called ISAT method. Let's see. One of the issues here is that you need a lot of particles. The convergence, the statistical error that you get, you can imagine if I have only one particle, I can't build a PDF of it. Okay, and if I have not enough particles, then my PDF is not very smooth, and you have statistical errors. And the convergence goes with n to the 1/2. So, you know, if I want twice better, more accurate solution, I need 4 times as many particles. That's one of the issues here. If you do this in 3D, in LES, for example, you do this in 3D, you need really a lot of particles. That's a problem. If you do this in RANS, when people do this in RANS, they don't use that many particles, but if you do RANS for a statistically stationary flow, you can also take this in time. You just let it go for some time. You don't have many particles, but because statistically stationary, you can just evolve, you know, this over time, and then that then gives you also good statistics. But if you have a time-dependent problem, then you just need to have many of these particles everywhere in the flow. Okay, one word about mixing models. I said earlier, so this here now should have this also is a 1 point. See, this is a 1 point equation. It evolves, this is for one particle, so you have this space, and then in this space you have, let's say in the 3-dimensional space, you have one particle that carries, you know, this information, these mass fractions, and now you need to integrate its composition over time, and you don't know what the neighbors are, so you don't know any local gradients, but you have a mixing term, you know, you have diffusion. And so there are different mixing models, and one is, as I said, is called interaction by exchange with the mean. What this says is that all particles go towards the mean because of diffusion. That makes sense, because if you have a box and you have an unmixed scalar in the box, let's say you have fuel on one side and you have air on the other side, and you let it stand for 10 years, then it's all the mean. You know, every point has the mean concentration. And so the PDF always goes to a delta function at the mean. And so here what you do is you evaluate the mean, you know, in your cell, or the surroundings of your particle, and then you have a time scale here. The time scale here, that somehow corresponds to the scalar dissipation rate, or the inverse. That is usually comes from some estimate for the scalar dissipation rate, because as we know, that is the local mixing rate. And you know, and then this just mixes with the time scale, and it goes towards the mean. And that has some problems, because you can imagine, think of infinitely fast chemistry. Let's say I have a particle which is rich, okay? But let's say the mean, locally, the mean is very lean. Then I mix this, so I move it towards the mean. But maybe it jumped across the flame front. It jumped past stoichiometric conditions. But for infinitely fast chemistry, you have chemistry only at stoichiometric conditions. So now the fuel was in the rich side, the cold rich side. Now it's in the cold lean side, and it never burned. Okay, so that's a problem, and people have thought about it and came up with different models, and yet different models, and so on. So the different mixing models, this is still what most people use, because it's very simple. Okay, so this is a simulation that we have done using this model. This was for 2 different jet flames here. This is the Sandia flame series, flame D and flame E. You see here the dissipation rate. You see a lot of local structure, and you see how this here translates into the temperature. And you see you get local extinction here in this flame E, low temperature regions, and not so much local extinction here in this flame D. Interesting is, I said this is very expensive. This was at the time when NASA got a new computer, Columbia, and the first days they had this computer, nobody was able to use it for some reason. And Venkat Raman, who did these simulations, he did a lot of work to make sure our code runs on that machine. And then we had this at the time, I think, was the fastest supercomputer in the world, or maybe number 2, but it was right up there. And so we had basically the whole machine for like 2 weeks, because nobody could figure out how to use it, and that's how we did the simulation. So even for jet flame with detailed chemistry, this is very expensive. But on the other hand, you see this here is conditional data. These are experiments here. The symbols and the lines are from the simulation. You see temperature here for this flame D is not bad. This is close to the nozzle, it's a little more downstream. It's not perfect, but it's not bad either. This is oxygen. This should be the air stream here, and this is the fuel stream, and you see there's some oxygen here in the fuel, and that's okay. And so this, but this should basically, oxygen should go to 0 here, and you see it does get very small. But then in this flame E, we have a lot of local extinction, so the oxygen should not go to 0 anymore because it doesn't burn in some regions, and so it's left over. And you see that here with this method, we were able to predict this, and this comes also from having the right models for dissipation rate and so on, which, as I mentioned, is an important quantity for this mixing term. Okay, any questions about this? Yes?
So when you have your PDF method, does it only assume Gaussian PDFs, or can you allow for any?
It doesn't assume any PDF, okay, because it's computed. The PDF is totally computed, right? Okay, so in a sense, what we did so far was we said, let's first talk about the models that don't even say very much. It should be premixed or non-premixed. You know, some of these methods up here, these simple methods, we said they're made, actually they're constructed in a way that they should work in both the premixed and the non-premixed regime. If they do or not is a different question, but that's at least the idea behind it. And also this transported PDF model, you saw that is, it didn't say premixed or non-premixed. On the other hand, though, it also doesn't take remember earlier we said the local interaction of the chemistry and the flow, it follows some certain physics. And if we look very closely to the structure of the flame, even in turbulent flames, then we see, you know, there are different regimes. And so this model also doesn't take these regimes into account. So somehow, magically, this mixing model should do all these things. And but you don't specify it, you know, premixed or non-premixed should do all of these things. So now we'll talk about models for premixed combustion, and then afterwards we talk about models for non-premixed combustion. So for premixed combustion, people have used so-called flamelet models. Flamelet, again, means the chemistry is fast, not infinitely fast, but it's kind of fast. And for premixed combustion, this means then the flame is thin compared to some degree compared to the turbulence. And the Bramos-Libby model, that's a nice model because it's, you know, you just see the general idea of how to do this. You see this relatively easily, and most of the models that are used for premixed combustion, they're very similar to this. And so the way we start out, we introduce a progress variable, could be the temperature, could be a product mass fraction, but the progress variable is defined such that it roughly varies between 0 for unburned to 1 in the burnt region of the premixed flame. And then we can write a transport equation for this. So imagine this is a temperature. It's easy to write a transport equation for this. And we take the mean transport equation. Then you get two unclosed terms. One is the scalar flux term. The other one is the chemical source term. And we need to see what we do with these. We said earlier, what do we do with the scalar flux term? Yeah, gradient transport assumption. Okay, and the gradient transport assumption, basically what it says is you have a gradient, and the transport, the diffusion, you could say the diffusion process now goes always downhill of the gradient. Okay, the flux always goes downhill of the gradient. Now this is an interesting thing because for premixed flames, if you do experiments, you evaluate this term in certain regimes, what you will find is that the flux goes uphill of the gradient. Okay, that's called counter-gradient diffusion. That is actually interesting because it shows you I mean, you would think it's not possible. But it shows you how complicated sometimes the interaction of the chemistry and the flow field is. You know, it just leads to the fact that the scalar flux goes uphill, goes up the gradient, okay? So, the point I want to make just is not so simple for this particular case. Anytime you have chemical reactions, combustion, you always need to think twice if these models are good or not. And what's the difference here? We said for the mixture fraction, we said, you know, we just use a gradient transport assumption, and that's pretty good. And here, we say we don't. And I said, you know, if you have combustion, you need to worry about, you know, think about twice. For the mixture fraction, we didn't think about it twice. We just said that's what it is. Why did we do this for the mixture fraction and not for this? Yes, so the mixture fraction doesn't have a chemical source term. So it's influenced by combustion, maybe because there's, you know, heat release or whatever. But the heat release changed the density changed the velocity field, and the velocity field then changes mixture fraction. But here, of course, we have a chemical source term right here. And we said earlier, in combustion, very often the chemical source term is not independent of transport at all. They're very strongly coupled, and they influence each other. Okay, so the assumption here of this model is that the chemistry is very fast, and then the flame front is very, very thin. So this model here really is formulated in what we called earlier the corrugated Flamet regime, where the reaction zone is very thin, and then the smallest eddy, even the Kolmogorov size eddy, is much larger than the entire flame. Okay, so that's how this is formulated here. You have here's burnt, here's unburned, and then you know this burns normal to itself, and then all the fuel conversion happens in a very thin front. So in the flow field, if I evaluate the PDF of C, of the progress variable, you know, I do many, many measurements, and let's say the flame is very, very thin, then I will get a high probability of finding unburned, and maybe I also get a high probability of finding burnt, but there's a very low probability of finding something that's in the flame sheet, that is between 0 and 1, okay? Because the flame is so thin, the volume is basically 0, and so it's a very small likelihood that I do a measurement that's exactly in this volume. So intermediate states between 0 and 1 are very unlikely, and then we can say, okay, if that's the case, then we can model the PDF of the progress variable. We can model it as two delta functions, because you will, when you do these measurements, you will always find unburned or burned. And so unburned would be C equal to 0, and burned is equal to 1. So you will find two delta functions. And depending on where you are with respect to the flame, you will find more burnt or more unburned. And that is here in these coefficients, alpha and beta. Alpha and beta, of course, they have to add up to 1, because the integral of this, because of the normalization condition of PDFs, the integral of these has to be equal to 1. And so there's one unknown here, basically, alpha or beta, and that unknown then tells you how much unburned and how much burnt states you have. So this is, again, the definition of the delta function. Okay, so this is how this PDF then looks like. Let's say this is the flame here. Okay, this is unburned, this is burnt, and then let's say you're very far away from the flame. Then, of course, you will get a delta function at C equal to 0. If you're very far in the burnt, then you will get a delta function only at C equal to 1. But if you're getting closer to the flame, then you get a little bit of unburned here. If I start in the burnt region, you know, if I'm sitting here right at the mean flame front, I should get 50-50 burned and unburned, and so on. So that's how this thing looks like. And so by just assuming the flame is very thin, I can easily construct my PDF. And we said earlier, you know, once you have the PDF, you can get all the moments of these. So now this means I can get the mean of C, I get the variance of C, and all these things. So I can use this okay, so that's the PDF. And then let's talk about this turbulent transport again. The turbulent transport term, the scalar flux term, it looks like this. And now, since we have the PDF, or at least we have a model for the PDF of C. We can see we can use that to model the scalar flux term. So this equation here we had earlier, let's say we have a function of U and C, and let's say I have the joint PDF of U and C, then, you know, with this I can get any moments of this function. And so U prime, C prime, that is of course this function now. So let's see what do we do with this joint PDF. We said earlier a joint PDF of two variables, you can write it using Bayes' theorem as the marginal PDF of one times the conditional PDF of the second condition on the first one, okay? So f of U and C, okay, that's interesting to know. What is the install update? No. Might be later. Okay. PowerPoint should know that we are working. We don't want to know this now. Anyways, so we need this. So f of U and C is equal to f of C times f of U conditioned on C. That's just Bayes' theorem. And f of C we know, and then f of U conditioned on C, that is this conditional PDF here. And so what we do then is you just plug all these things in here, and you get a function here like this. And then if I plug this in, I can just solve it for this. I'm going the wrong way. So then I get, with some assumptions, I get an expression here for the scalar flux. And what you see here is that it looks, it looks different from a gradient transport assumption. And what's interesting then, especially if you look at this C times 1 minus C, C, of course, is it varies between 0 and 1. That's how we defined it. So C times 1 minus C, that is always larger than 0. And then you always have an acceleration of the velocity through the flame, and that means that UB is larger than U unburned, and you see this also larger than 0. So this is always larger than 0. This is larger than 0. So if you look at the gradient transport assumption here, let's say for this case, then the flux here would be negative. This is positive, and with a minus sign, this would be negative. But as a matter of fact, this is positive. So this shows you the counter-gradient diffusion aspect. Okay? And this is a model one could use, but one needs to keep this in mind. Interesting is that, so the question is, why do you get this? And you get this because, and that's another interesting fact here. When we look back, why do you get this counter-gradient diffusion? We look back at this equation. We have a U prime and we have a C prime. And we say the U prime and C prime, what are they? They are turbulent fluctuations, okay? But really, they're not, the turbulent fluctuation now for this premixed flame means something else. It's not just that you have, a quantity that fluctuates. You have that also, but you have the whole flame that because of the velocity, the fluctuating velocity field, goes like this maybe. So if I do an experiment right here, then sometimes I measure burnt and sometimes I measure unburnt. So I get this, so this variation from burnt to unburnt, that's not a turbulent fluctuation, that's just what the flame is. But sometimes I see this part of the flame and sometimes see the other part of the flame. So that, of course, comes in here. For example, the density and also the U and the C, they have huge jumps across the flame front. And so this heat release aspect, that makes the heat release aspect, that makes seemingly this flux or the mass flux go the other way. So, okay, so that would be That would be a model for the flux, and now we need a model for the chemical source term also. The chemical source term. So the interesting here is that if you would just take the source term and compute the mean source term with this, then it would be 0. Because the source term is only 0 if C is not equal to 0 or 1. If C is 0, there's no source term because very, very small because the temperature is so low. If C is equal to 1, there's no fuel left, right? So you get source term only for values in between, but our model for the PF, it excludes any values in between 0 and 1. Okay, so that's in our assumption, that's the wrong way to close this term. So here we close this term in a different way. Just like we said before, we can say the mass burning rate as function of time is equal to the area times the burning velocity. That gives you a volume per function of time, and then that times the density, that gives you a mass per unit time. Okay? And because this is mass per unit time and volume, that's what the source term is. We take here not the area, but the area per unit volume. Okay, so this here is the area per unit volume, and then so this here gives you then the mass burning rate per unit volume. And so now so that's what we said earlier, and that's easy to understand. The question is, where do we get this from? That's the first question. And then the second question, what's this I0? I0 first, we said earlier SL, so this SL naught, this is just the unstretched laminar burning velocity, but then we said we have stretch effects also and things like that. The turbulence influences also the laminar burning velocity, and that is this I factor, here's a strain factor, that just accounts for the modification of the local burning velocity by the turbulent velocity field. So that is that. How large is that? You have to think about it. You have to come up with, there are different models for this, but it's not so easy to model this. And then this one here, there are different ways to find to find closure for this. There are algebraic models. This one here is an algebraic model where you just say this is proportional to C times 1 minus C divided by some crossing length. That's just dimensionally that is right, and it gives you some solution. This Ly, you have to think about what this is, but this would be an algebraic model. Typically, people solve transport equations for this. Transport equation for this, you can derive a transport equation for this. This is a very lengthy, very hard to close transport equation. So here what we do with this basically is like with the epsilon equation, is empirical. You just say I have a time-dependent term, a convection term, and a turbulent transport term, and then I have a production term and a dissipation term, a production term that produces a flame surface, and a dissipation term that takes the flame surface out. And this is, these are just, again, by dimensional arguments. These are closed. So this here is very, very similar to the production term in the epsilon equation. Just instead of in the epsilon equation, you have d epsilon dt, and then here you have epsilon squared by k, and here you have d sigma dt, and so here you have epsilon over k times sigma. I mean, the form is exactly the same, okay? And or the k equation for that matter. And then the dissipation term here, basically the idea is how is flame surface dissipated, or how is it taken out? We said earlier it's taken out by burning. If you have a flame that looks like this and you burn it for a little bit, it will be all flat because all the wrinkles, they will just burn out because the flame propagates normal to itself. And so there should be some burning velocity here. That's kind of the idea. Okay, so you can solve this, and that gives you then the value for sigma. Interesting here in this equation is that this equation really gives you the limit of infinitely fast chemistry. That's a subtle thing. My question to you is, if I make the mixture more lean or more rich, does that equation or does that model, the general model, is that sensitive to this? Would the model see that the mixture is very lean now, for example? Okay, what do you think? Mm-hmm. That's actually, let's say, that's the expected right answer now, because you have a flame speed there. So you would think, yes, it's captured. But the right answer is no. The model doesn't know anything about the equivalence ratio. Why? Because look, this is the source term. The source term is proportional to SL times sigma. Okay? So let's take this value SL times sigma and call it F or G. G, because F we have it already. G. Okay? Then if I multiply this equation by SL in every single term, then you see I have SL times sigma, SL times sigma, SL times sigma, SL times sigma, SL squared times sigma squared. So in every single term, I have G. G, 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 G squared. Okay? So if I solve this equation for G, it doesn't know anything about the burning velocity, and I can just use that G in the other, plug it in here. And I never had to specify the value of the burning velocity. Okay? So the burning velocity appears in two different places, and it just cancels each other out. Okay? So this model doesn't, the way it's written here, this doesn't know anything about, equivalence ratio, the chemistry, and so on. So this is really the infinitely fast chemistry limit. Okay, good. So why did I show you this model? What I wanted you to get out of this is, first, if you have a chemical source term, these equations might do funny things. Okay, that's number one. If this counter gradient diffusion term is modeled like what I showed you here or not, that doesn't matter too much. It's just the point is just to make that it does funny terms. The flame surface density model, that's a model that's very often used in different flavors, but it's all this, but just little different flavors on how this equation here is written, how this I0 is modeled, how what different terms appear in this equation, and all of this. So this is just the basis foundation for all the flame surface density models. Okay. Okay. So the next one then here is the level set model, and I should point out what one of the big issues of this model is, and that's particular to LES. If you just think of RANS, is not a problem. But if you think of LES, one of the problems here is that for this now, what do? We solve a model, we solve an equation for a progress variable. Okay? The progress variable in LES now, in LES, if I have let's say I have a jet flame like this, or the turbulent Bunsen flame like this, and now I look at the progress variable along this line. Okay? Then how does the progress variable look like? You see here, it's all, so this is instantaneous. Here it's all burned, okay? And here it's all unburned, and here it's all burned, okay? So the turbulent velocity, it kind of looks like this, whatever, but the progress variable, it really looks like this. Okay? Maybe the flame shape is complicated, I get multiple crossings, then maybe it looks like this. But, very, very similar to this. So the point here, so this is instantaneous. If I filter this now, so let's take the multiple crossing out. If I filter this, it look like this. Very, very similar. And if my filter is the same as the mesh size, then you see I don't resolve the change from 0 to 1. That's a problem. If the flame is thin in this corrugated flame regime, the filtered front still has a jump. And if you have a jump, you need to do something in numerical algorithms, you need to do something advanced to track the movement of this jump. You need to do front tracking, or you need to do shock capturing, or whatever you want. But you need to do something to make sure you're not getting too much diffusion, because, as you know, diffusion is a part of what drives this thing. If I have numerical diffusion, it moves at the wrong speed. Moves at the wrong speed means my solution is wrong, because the flame speed is exactly what you want. So that's why in LES we use this level set method. The level set method is nothing. It's not a model really. It's just a numerical technique to deal with a jump like this. Because the level set for this, remember, the level set is defined like this. The level set says at the flame front, at the position of the flame front, the level set function is 0, and it is negative in the unburned, and it's positive in the burned, and it can be defined like a distance function. So this would be the level set function. It has no jump across the flame front. It's just smooth. And if you know this, if you know these values, you can say, okay, whenever this is negative, you know, I make it, whenever this is negative, you know, I have the unburned density, and whenever it's positive, I have the burnt density. That's kind of the idea. So let's look at the level set function. Some of these slides we have looked at before, so it's not new. Just repeat it here. This is how we derive the equation. We say we want to have the G function at the flame front. It should be 0. And then dg dt here at the flame front is 0. The change of G at the flame front is 0 because it's supposed to be always a constant. And I can write this like dg dt plus dx dt dg dx is equal to 0. And then this dx dt, that's just the movement of the flame front. That is this here, so I can plug this in, and it will give me a solution to this. Now, I put this here because the level set methods, actually, they were developed for computer graphics. You see this is an animation that is used, you know, in movies, and so this here is the surface here. That's just using a level set function. And then they, you know, somewhere they put some particles here to mark the spray. But basically all this stuff here is all just level set. Okay. So we use the level set function also to do simulations in, you know, for multi-phase flow like this. I mean, this is just you know, make it look nice, but we use it also for you know, real simulations of let's say diesel sprays or something. So this here is from the group of Ron Fetkow at Stanford, who you know, works in this computer animation business. So, oops. Okay, so if I plug in this dx df, then we get this equation. We had derived this earlier. This has interesting. The solution to this, I mentioned this earlier, is not so trivial. It has no diffusion term. It can be applied to thin flames, and I mean, especially in this limit, this is very good. And you need a well-defined burning velocity, which means your local extinction or something, and you don't know what the burning velocity is for that. Then, well, local extinction, it wouldn't be in that regime anyway. So, okay, so it should be applied here for the corrugated flamelets regime. Let's see, what does this say? Well, as I mentioned the last time, so this is interesting, because most of the equations we have, they are conservation equations. They're based on some conservation principle. The momentum equation is based on conservation of momentum, temperature equation, conservation, first law of thermodynamics, conservation of energy, momentum equation, and so on. It's all based on conservation principle. This is not based on any conservation principle. It's just kinematic. We just say we have a front, and that moves with a certain speed, and it should be tracked by this function here. And so it has no diffusion term, and so it's a little hard to solve. It's valid. It was derived only for the for the surface. So if you define this as a distance function, then like I did here, then there's nothing in this equation. We didn't put that information in the equation, so it will not preserve that property. So what you do is you solve this for one time step or for several time steps, and then you do what's called a reinitialization, where you solve an equation like this. This here is so basically this g dx equal to 1 means g is equal to x. It's just the distance, gives you the distance from the flame front. So this is the so-called reinitialization, and a numerical method like the so-called fast marching method, and so on, to solve an equation like this. Okay, the burning velocity here, it can be influenced here by strain and curvature, Lewis number effects. You can use this expression here, and we discussed this earlier. There's an expression here also for the Markstein length here. So you can put all this together, and there are fits also for the Markstein length for certain fuels. And you get a G equation or Levitt equation here. It looks like this, and it also considers the effect of the the modification of the flow on the burning velocity. Okay, so let me just say this here, and then we'll take a break. What's interesting here, we said this is valid now when you have a very thin flame, but we said for in the thin reaction zones regime, the turbulence doesn't disturb the inner layer, but it does mix in the preheat region, and you might get something like this, where this is the inner layer, but then the preheat region is broadened, and then you need to have more information than just the than just assuming an infinitely thin flame. So in the thin reaction zones regime, we need to do something else, and so that's what we're going to do then after the break. So let's take a break here.